Welcome to in this video. Today we will discuss about the transport layer. So, let's start the video. The transport layer is the fourth layer in the OSI, Open Systems Interconnection, model and plays a crucial role in facilitating end-to-end communication between devices. Here's an in-depth look at its functions and key concepts. Primary function. The primary function of the transport layer is to ensure reliable, end-to-end communication between devices. This involves managing the data transfer between systems, providing error recovery, and ensuring data integrity and proper sequencing. Key functions of the transport layer: segmentation and reassembly. The transport layer breaks down large data messages from the application layer into smaller segments that can be transmitted over the network. At the destination, these segments are reassembled into the original message. Error detection and correction. The transport layer ensures that data is delivered correctly by detecting errors in transmission and requesting retransmission if necessary. It can handle both error detection, e.g., checksums, and error correction. Flow control manages the rate of data transmission between sender and receiver to prevent overwhelming the receiver. This ensures that the sender does not send more data than the receiver can process. Connection establishment and termination. For protocols that require a connection, e.g., TCP, the transport layer establishes a connection before data transfer begins and terminates it when the transfer is complete. Data sequencing ensures that data packets are delivered in the correct order. If packets arrive out of sequence, the transport layer will reorder them. Multiplexing and demultiplexing allows multiple applications to use the network simultaneously. Multiplexing combines data from different applications into a single stream, while demultiplexing separates it at the destination. Transport layer protocols. Two primary transport layer protocols are used in modern networks: Transmission Control Protocol, TCP, connection-oriented. TCP establishes a connection between sender and receiver before data transfer begins. Three-way handshake. Reliable ensures data is delivered accurately and in the correct order through mechanisms like acknowledgements, ACKs, retransmission of lost packets, and checksums. Flow control uses a sliding window protocol to manage the amount of data sent before requiring an acknowledgement. Congestion control adjusts the rate of data transmission based on network congestion to prevent overload. Stream-oriented provides a continuous stream of data between applications. User Datagram Protocol, UDP, connectionless. UDP does not establish a connection before sending data. It simply sends packets, datagrams, to the destination without ensuring they are received or in order. Unreliable. There is no guarantee that packets will arrive or be delivered in the correct order. No acknowledgements or retransmissions are provided. Low overhead. Because it lacks the mechanisms for reliability and ordering, UDP has lower overhead and is faster than TCP. Suitable for real-time applications. Often used for applications where speed is crucial and occasional data loss is acceptable, such as video streaming or online gaming. Ports and sockets. Ports. The transport layer uses port numbers to distinguish between different applications on the same device. For example, HTTP traffic typically uses port 80, while HTTPS uses port 443. Sockets. A combination of an IP address and a port number creates a socket. Sockets enable communication between applications over a network by providing a unique endpoint for data exchange. Flow control and congestion control. Flow control manages the pace of data transmission to ensure that the receiver is not overwhelmed. TCP uses a sliding window mechanism for this purpose, where the sender must wait for acknowledgements before sending more data. Congestion control adjusts the data transmission rate based on network conditions to avoid congestion. TCP implements algorithms like AIMD, additive increase, multiplicative decrease, to dynamically adjust the rate of data transmission based on feedback about network congestion. Error handling. Error detection. Both TCP and UDP use checksums to detect errors in transmitted data. If the checksum does not match, the data is considered corrupted. Error recovery. TCP includes mechanisms for error recovery, such as retransmitting lost packets and using acknowledgements to confirm receipt of data. Applications of transport layer. The transport layer is essential for a wide range of applications, including web browsing. Uses TCP to ensure reliable delivery of web pages and resources. Email. Protocols like SMTP, Simple Mail Transfer Protocol, for sending emails, and POP3, Post Office Protocol, or IMAP, Internet Message Access Protocol, for retrieving emails, rely on the transport layer. Streaming media. Protocols like UDP are used for streaming audio and video where low latency is crucial and some loss is acceptable. Online gaming. UDP is often used for its low latency characteristics, although some games may use TCP for certain types of communication. Summary. In summary, the transport layer is vital for ensuring reliable, efficient, and organized data transfer between devices across a network. It handles segmentation, error detection, flow control, and multiplexing, with TCP and UDP as its primary protocols. TCP provides reliable, connection-oriented communication, while UDP offers faster, connectionless communication suited for real-time applications. Understanding the transport layer's functions and protocols helps in designing and troubleshooting networked